Hi everyone, my name is Tejas Chopra, and today I'll be presenting Cloud Microservices for a Billion People. I'm proud to be talking at the Cloud Day 2021 conference. Thank you to all the sponsors and partners of Cloud Day 2021. The agenda for my talk is as follows. I'll go over a brief introduction about myself, what I do. We'll get into the problem space definition, explaining the problem that I was trying to solve, how I went about defining the requirements and ideating a solution, some of the design choices made during the process, and how using agile practices and designing iteratively was very beneficial in building these microservices. Finally, some results and takeaways. The picture here shows a typical picture of a retail store in India. And as you can see here, it's very fragmented in nature, and you will see towns and cities littered with thousands of such retail stores. Uh, my solution was trying to solve the food wastage problem from the retail stores. A brief introduction about myself. I started my journey in the year 2010 when I came to Carnegie Mellon University for a master's in electrical and computer engineering with a specialization in computer science. From 2012 to 2016, I worked at companies such as Apple and Samsung, where I primarily worked on distributed systems. In the year 2016, I joined a startup as the first engineering hire. We were trying to build a marketplace for fast-moving consumer goods. You can think of it like Amazon, but in this case, the buyers are wholesale traders of FMCG products, and the sellers are retail shop owners. The goal was to build software for the masses and for a domain where technology had not previously been used. In the year 2017, I joined Datrium, where I was working on distributed file systems and storage. And then I joined Box, where I was working on replication, cloud storage, and file systems. I moved to Netflix in 2020, where I'm a part of the data storage platform team for Netflix Studios and streaming platform. My job is to architect microservices and infrastructure solutions to support the exabyte scale data that is produced and managed by Netflix Studios and streaming platforms. Let us get into the problem space definition first. The problem we were trying to attack was fast-moving consumer goods. These are actually packaged goods, beverages, food items, cosmetics, etc. In India, you will find towns and cities that are littered with millions of these mom and pop shops. So they are small and medium enterprises compared to the Macy's and the Targets that you find in the US. The market cap for this industry is 50 billion US dollars per year. In the traditional sense, the buyers are retail shop owners and the sellers are wholesale traders. As you can see, there are very few sellers, but a large number of buyers that serve a population of more than a billion people. Now, the problem in this space is that there is a lot of wastage, and just the food wastage is quantified to be around 70 tons per year. So, if we can create a dent in this space using technology, we can avoid food wastage. And there are several reasons for this wastage. Number one, the last mile delivery is very untimely and results in wastage of perishable items. There is no feedback mechanism from the buyer to the seller, and there is no good way to capture feedback from the end users of the product as well. There's no good way of maintaining a catalog of items in the store. So that too results in a lot of wastage. And finally, there are deeply entrenched relationships between buyers and sellers. So the buyers do not have the means to explore the other sellers for better offers or faster service. What if we could prevent this food loss? What if, like Amazon, we can create a marketplace with wholesale traders on the one end as sellers and retail shop owners as buyers? What this will give is buyers a choice and sellers a platform to expand to other buyers. Choice is always good, but because it will help uncover better deals, timely deliveries, and better user experience. And the feedback mechanism can be integrated into the product itself so that the users can have the ability to search for offers. To remove the issues with last mile delivery, we will handle the shipping. And since this industry will almost always deal with bulk orders in a transaction, the shipping costs get amortized pretty well. Finally, since we are attacking a domain where users are not very tech savvy, it is important to build an empathetic user experience from the ground up. This is something that I focused on, and I use technologies such as Elasticsearch, Kafka, DynamoDB, Redshift, and also Dropwizard frameworks to develop these microservices. This was a critical piece in our journey. Now let us get into some of the challenges of this industry. The number one challenge was that we were trying to attack a domain where the users had never used a smartphone. They were well accustomed to using feature phones. So how Android apps work, how the App Store runs, and in general, the memory, the battery life of the smartphone, they were not very well versed with it. We had to build something or build an app that used very limited battery life because this industry works on very thin margins where every penny saved actually goes back to the pocket of the user. Our users were not very well versed with English language, so the products had their text written in English and had to be changed and localized into local languages so that the users can read them and understand the product. Concepts of an Android app that we are accustomed to, such as cart, order history, and order tracking, were very new for our users, so we had to educate them about it. And there were a bunch of other challenges with trying to understand the user's experience and build empathy for the users. A great example is product images. If you typically go on Amazon, you will have a product that has an image, and there is a lot of text associated with the product, such as attributes of the product and the different variants. For our customers, they really wanted bigger images, but they didn't care so much about the attributes or the text of the product. And so dealing with that in one of the iterations was again a critical part of our journey, trying to build a better user experience. Whenever you start building any software, it is very important to define the requirements before you start coding. And if you look at a marketplace, the table stakes for any marketplace today are you need the ability to search for a product and browse the product to get the relevant information. You need an order management system that can have cart, order history, and tracking. You need some form of authentication and authorization and notification mechanism. The ability to sift through different offers and then also pick an offer for a product. And finally, on the other side of the table, allowing sellers to have a portal where they can ingest products, review the orders of the day, place or like take invoices and shipment information. All of that is very important for building any marketplace. And here are some of the design choices that we went with. We decided to go cloud native because cloud provides ease of scale, ease of manageability, pay per use, and is ideal for bootstrapping an idea. We leveraged DynamoDB, NoSQL database for our products, orders, notifications, and shipments. The data was unstructured initially, and we wanted to use DynamoDB streams, which would stream any changes to the table into different services. We dabbled between using Kinesis and Kafka for event handling and asynchronous processing that would populate our downstream services such as Elasticsearch and our Redshift clusters. Finally, we needed a way to capture metrics to get customer insights. For example, what are the products that they are adding to their cart? What products are ordered together? And what products are ordered more in a particular month of the year? And that insight is then served to our sellers so that they can procure items in advance. And the way we went about architecting the system is that we used agile practices and we started developing services iteratively. So the first particular iteration was to see the product market fit. And this was a pilot that we ran. And it was a very simple pilot. It was an SMS-based solution that works on feature phones. So each morning, an SMS would be received by our customers that would contain all the images of all the products and the quantities to place an order. Our customers would scroll through the entire SMS, pick products that they would want to order, and then place a response to the SMS. This and to implement this, we just use an AWS Lambda that would then query the product information from DynamoDB tables where product was ingested by the sellers and then return that information to the user. And finally, a human would vet the responses at the end of the day and mutate the DynamoDB table directly. This scaled very well for up to 10 stores. And we realized that Lambda works very well for time delivery of messages. But human vetting is painful. It must be replaced by programs. And this approach is very rigid. There is no offers, no real-time quantity updates, no search or browsability. And this was just really a POC or a proof of concept for us to know if there is a product market fit and whether our customers would like something that can be provided to them at their fingertips. And we saw that there was a huge surge in order just by this pilot. We were doing more than $500 revenue per day. Then we realized that we need to separate out the seller portal from the buyer's app. And we focused a lot on that part of the development in our first iteration. So our seller had a separate portal and a separate set of microservices than the buyer's app. It was initially a monolithic service for the seller and just an AWS Lambda for the buyer. And what the Lambda was used for is that whenever an order was placed through our Android app, which was a very generic app, and it would again have the same interface as the SMS, where users would scroll to find a product and swipe right to place an order. On order placement, a Lambda would be invoked. The Lambda would go and mutate the DynamoDB tables like it did with the SMS as well. And sellers could ingest products and get invoices from DynamoDB tables directly. This was very quick iterative development, and we were able to do up to 500 orders per day. It only worked for single orders because there was minimal state management, no concept of a cart. And one thing we realized is that the Lambda has a very slow warm-up time. So order placement is very slow in this process. We went to the second phase of iterative development where we removed the Lambdas completely and we replaced it with an EC2 instance that had our monolithic service running. The monolithic service for the buyers was interacting with products, order management system, authentication, and notification. And for the sellers, it was dealing with products, invoices, and offers. The framework we used was Dropwizard framework to develop this monolithic service. At this point, we did not still have the browse and the search capability. The users would scroll down to find a product and swipe right to place an order. There was no concept of a cart added yet. One thing we did do is we tried to take images of the products in local languages. So localization was now a part of our product. And the other thing to note is that at this point, we did not have browsability or searchability because we did not define relationship models. I will get into details of what this relationship model is and how is it different in our domain as compared to, let's say, B2C products that are sold on Amazon. Uh, and finally, we realized that our monolithic service does not scale beyond a point, so we moved to microservices. Monolithic services are difficult to modify, test, and release. When you have multiple databases that your service is talking to, there is a lot of mixing of business logic and no clear separation of concerns. There is no fault domain, which can mean that if one of the tables or one of the parts of your service goes down, your entire service will go down. So that was the reason that we wanted to split the monolith into microservices. We split it into multiple services such as product, order and cart management, notification, and invoice. And one thing to note is that sometimes we have a tendency of splitting a monolith into multiple microservices based on the number of tables we have. So we will probably have microservices that have CRUD APIs on each table. That may work initially, but I think that over a period of time, that may result in a lot of microservices. And the problem with a lot of microservices is that intra-service communication can exhaust the network connections. And for just getting one result out to the user, you may end up contacting tons of microservices on the backend. With each microservice, you will actually have an additional hop of latency. So that may actually harm the user experience. So you would always want to be mindful of how many microservices you create on the backend. It has become more of an art than a science at this point. Along with that, if you notice closely, we now have downstream services powered from our DynamoDB table. So in a lot of databases, there is a new concept called change data capture, where you would like to see what are the rows that are changed in the database and capture events that can reflect that. These events can then be used to power downstream services. We leveraged Kinesis data firehose to capture all the events from DynamoDB streams, and the event payload was then used to index different types of indexers. In this case, in this example here, I've shown three indexers. There's a catalog indexer which is indexing any change that is initiated by the seller on the app. So when the seller changes the product image or adds a new offer, it goes to the catalog indexer and then gets reflected on the Android app. The second one is the Redshift indexer, which is used for any analytics and metrics captured from the user. So when the user scrolls on the app, we capture different clicks and scrolls, and we capture the browse history of the user. And these metrics are then forwarded to the Redshift indexer and populates different tables in Redshift. And Redshift is a data warehouse on Amazon. The third one is the Elasticsearch indexer. And this is used to really power our browse and search capability. And on product changes or on ingestion of new products or brands or manufacturers, Elasticsearch indexers will populate the appropriate indexes, and that will be reflected in the user's search and browse features that we expose. I mentioned that we use Dropwizard for cloud native microservices. Dropwizard is a framework that contains Jackson, Jetty, and Jersey. Jetty is an HTTP server inside the main method. Jersey will map the REST request to Java objects. Jackson is used for JSON serialization and deserialization. In Dropwizard, you have to create a resource class, register the class, and implement methods. And if you see here, this is a simple example of how a Hello World service would be implemented in Dropwizard. You have the Hello World resource class here, and you will have a get method which is timed so that you can know the latency of saying hello. And then you can pass it query parameters. You can also say like put a path and the type of information it produces as an annotation to the class. Metrics and health check are all first-class citizens in Dropwizard, and they are configured. I could have used Spring Boot as well, and the advantage of using Spring Boot is that dependency injection will come built in. So a lot of the code gets very simplified, and you will write less code for more tasks using Spring Boot. Let us now start to understand the domain more and the problems that we faced in trying to build, browse, and search. So when you look at things around you, let's say your iPhone, you know that the manufacturer is Apple, the brand is iPhone, the product vertical is smartphones, the product line is iPhone 12, and the product is iPhone 12 with its IMEA number. For fast-moving consumer goods, the FMCG products that I'm talking about, these attributes are not always clearly spelled out. For example, if you look at this image here of Procter & Gamble products, you will be able to recognize some of them. The product verticals here are baby, feminine care, family, fabric. The product lines are diapers, kitchen towels. The brands are Tide, Ariel, and the products are finally Bounty paper towels, 33% extra large. So you can imagine, for a lot of food related items, the lines and relationships between these product attributes, such as manufacturers, product verticals, product lines, and brands, are very thin in nature. In order to give users the ability to search any product, there must be a way to get to the product. Our biggest challenge was that because these relationships were very dynamic in nature, how do we build a backend store to serve the complex nature of our queries? We needed the ability to search by brand, manufacturer, and some of the sample queries are listed below. So we want all the products that belong to a particular manufacturer and a brand, all the products that belong to a particular product vertical, and similarly a product line and brand. Instead of a tree of information, this is actually a graph of information at this point. And this is where Elasticsearch came to our rescue. With Elasticsearch, you can build an index and relationships that can help serve complex queries with extremely low latencies. You will get features such as autocomplete right off the bat, and is something that we leveraged a lot with our customers. So at this point, the app was somewhat complete in nature. We had a buyer side which had product search and browse. Buyers could place objects in a cart and place an order. They could view their order history and look at the order tracking using order management system. The sellers were able to ingest new products and update quantities for products. They could update offers. They were able to obtain all the offers, all the orders that were placed, generate invoices and shipments. So let us now move on to what were some of the results and takeaways from this learning. So in terms of technical learning, one thing is that DynamoDB is not the best database for relationships. I went with DynamoDB primarily for DynamoDB streams, but I should have used a graph database. Today we have alternatives such as Amazon Neptune, and also you could explore Neo4j that is backed by DynamoDB. So you can still leverage the event streams generated by DynamoDB, and it makes the job of indexers very simple. The second thing is I used Kinesis initially, but moved to Kafka later. Kafka allows faster retrieval and it stores data for longer periods of time. It has now developed and it has connectors for DynamoDB, Redshift, and Elasticsearch. It is managed by us though, and we have to take care of spinning up the Kafka cluster, maintaining the zookeeper, and all of those cluster management tasks. I did not explore using containerization, but using Docker and Kubernetes for any app deployment is a necessity in today's world. Using CI/CD pipelines to trigger Jenkins jobs and Spinnaker, which is an open source tool, open sourced by Netflix actually, can be used for deployment and monitoring. I did not explore using service mesh for microservices. Service mesh allows you to gain insights into microservice to microservice communication. It will help, it's a framework that can help detect the call stack. So you will exactly know which microservices are talking to which other microservices. You can detect for failures between communication of microservices, and it in general provides more insights and visibility into your networking infrastructure. These were on the technical side. On the product side, some of my learnings were as follows. So my customers were not very well aware with the concept of a cart. Even though I introduced cart, they would still swipe right and place an order. And for them, they would place an order at different points in the day when they are aware of a catalog item being sold. So on our end, we realized that they were actually placing multiple orders in the day and paying for the shipping cost of each order. Whereas if they would have placed all the orders in a cart, they would pay a one-time shipping cost. So what I did was I created a virtual cart on the backend so that all the orders that were captured during the day would make it to a virtual cart, and they would then pay the shipping cost of the virtual cart as if it was a single order. That led to a 27% savings in shipping costs for our customers. Uh, I focused a lot on enhanced searchability. So products have missing data, like some products may not have brand information or manufacturer information. I went and researched per product to ingest appropriate values, and this was driven by my customer interactions. This helped me build enhanced connections between products and were useful in allowing our customers to search and browse these products better. As per my estimates, this led to an increase in our orders by 24%. Data and metrics was a first class citizen in our architecture, and I invested in having a Redshift cluster right up front when we were designing and iterating through our processes. And this was because we wanted to capture as many metrics and insights from the customers as we could. Uh, we wanted to understand the customer insights that can help determine the seasonality of orders, and it would enable our sellers to procure items in advance for fulfillment. This led to an increase in revenue by 34%. But one thing to note is that it also led to an explosion of costs in Redshift. We went from $500 per month to $4,500 per month within 6 months. The results were that our sellers increased from 1 to 7, our buyers increased from 10 to 400. We were able to capture from 7,000 insights per second, metrics per second, to 780,000 metrics per second. Our revenue grew from $200 per day to $8,000 per day. And finally, we were able to help solve the food wastage problem by improving the efficiencies by 27%. The key takeaways for me as an engineer and as an architect for this system were that you should always build software for the customer. And this is important because what applies in one industry may not necessarily translate directly to another industry. It is important to understand the users, their experience with different softwares, and then show empathy in your architecture for these users. More code is more bugs. So the best way to reduce bugs is to write less code. There's a common adage that every 100 lines of code is a bug. So ability to write simple and lucid code to do the same task is very critical. As things scale, there will be failures. and you will have to deal with pains of scale. But you must always design systems in a way that you feel safe. And at no point do you lose the customer data. So for example, it is okay for one of the product's images to not show up, but it is not okay that an order is placed and it does not get reflected on the customer's app. Performance on smartphones is very critical. So designing your systems that can be mindful of leveraging caching on the smartphone and not using a lot of network connections can help save battery life and mean a better performance for the users. The other thing to note is that you cannot always just use a lot of memory footprint on the smartphones as well. So you need to employ strategies such as compressing and deduplication to reduce your footprint of data on the smartphones. Invest in learning about the business and the pain points and see if technology can solve some of them. For example, we realized that adjacent from our app, the customers did not in general have a way to catalog all the items in their store. And it was very easy to build on top of the order history because the history of all the orders would tell the customer what all items they have in their catalog. And so we built that solution for them and provided it as an extra freebie that was separate from our initial core product. And this was because we tried to solve the problem for our customers, and it actually helped increase the stickiness of our application. Data is gold, and invest in gathering insights from it right at the get-go. If you haven't designed intelligently for the cloud, your cloud costs will spiral out of hand. And this is what we realized with our data. So then we started using techniques of compression and deduplication on both on their devices as well as on cloud to reduce the cloud footprint and thereby reduce the cloud costs. That's my time. Thank you so much for joining me today. Please feel free to reach out to me on LinkedIn, my email address, and Twitter. Thank you.